Hello everyone, Mr. Fawcett back here with part 2 of our power rule for derivatives lesson. In the first lesson we worked our way up towards a definition of what the power rule was. In today's lesson we're going to look at how to apply it. So we're just going to look at 6 practice problems. Hopefully we have time to get through all of them. And all of these will use the power rule. We're just going to talk about some key differences between the different problems, and there may be some things we need to do the functions before we're able to apply the power rule, but we'll get there. As always, I encourage you to pause the video, try these problems on your own before coming back to look at the answers and explanations. So let's look at number 6. I have a function, polynomial function. I'm going to take the derivative. So my notation is f prime of x is equal to 12 because I'm multiplying the exponent by the coefficient. So 12x squared, because then I subtract 1 from the exponent. So you multiply the exponent by the coefficient and then subtract 1 from the exponent. With my second term, 2 times 5 is 10. Take away 1 from 2 gives me 1, or just x. Remember that this exponent on the x is 1. So I multiply 1 times the coefficient, which is 1. And then x to the 0 power is just going to be 1, so I just leave it. And then, of course, the derivative of a constant is 0, so you could put plus 0, but that's unnecessary. This would be a complete answer for number 6. Okay, let's look at number 7. Now, number 7 looks a bit different. It's a quotient, so we can't just immediately go and apply the power rule. We can simplify this, though, right? So we could factor out an x from the numerator and simplify it with the denominator. So let me rewrite this. So it's going to be equal to x times the quantity 3x cubed minus 3x minus 2 all over x. And I can simplify these x's. And we'll notice that when we come up with our new function, so when we come up with f prime of x, and we get 3x cubed minus 3x minus 2, we just have to say these are the same as long as x does not equal 0, because we couldn't have x equal 0 in our original because we have an x in the denominator, so I'd make the denominator equal to 0. But when we came up with the blue function, I would be able to just substitute in x and get a number. So we have to add the clarifier where x cannot equal 0. Oops. Now we can take the derivative. We'll come up here and we'll get f prime of x is equal to 9x squared minus 3. Again, if you're unsure of how I got that, I was multiplying the exponent by the coefficient, so 3 times 3 is 9, taking away 1 from the exponent, that's where I get my x squared. And then I use the same process for negative 3x to get negative 3. The final thing we should do is just make sure that we know that this derivative is good as long as x does not equal 0 again. So where x does not equal 0. Because we can't have a derivative exist if the original function is not continuous. And the original function is not defined at x equals 0, so it's not going to be continuous at x equals 0. You just don't want to have something like a question where it says find f prime of 0, and you just substitute 0 into your derivative function and you get negative 3. This would be wrong, right? Because we can't actually take the derivative at x equals 0. So we have to understand that our original function can influence the domain of our derivative function. And 0 is not in the domain of our original, so it can't be in the domain of our derivative. Okay, let's look at 8 and 9. If I look at 8, my f prime The only tricky thing about this is that we're going to be working with fractions, but again, we're in an AP Calculus class. We should be okay with that. Negative 4 times 3/4 is going to be equal to negative 3. If I subtract 1 from 3/4, I get negative 1/4. So it's x to the power of negative 1/4. 2 times 1/4 is 0.5, or you could write it as 1/2. It's up to you. 1/4 minus 1 is negative 3/4. Now, this would be an acceptable answer, except it says leave your answers with all positive exponents. So we need to know how to convert rational exponents. Whenever they're negative, we need to convert it to, well, we can do one of two things. We can convert to radical form, or we can just convert the exponents to positive. So f prime of x, we could say, is equal to negative 3 divided by x to the power of 1/4 plus 0.5 divided by x to the power of 3/4. And this right here fulfills the requirements of the directions. All the exponents are positive. Let's look over here at number 9. I'm going to erase some of this so we have some extra space. So number 9 also has a quotient for the first term. Now, once you do the power rule multiple times, and maybe a month down the road in this course, you may just be able to understand how it works even when you have your x term in the denominator. But I'm going to rewrite this so that we have no fractions, and then it's going to be a little easier to apply the power rule. So let's just rewrite that first. So I'm going to have f of x is equal to 2 times x to the negative second power minus 4x cubed. Now it's, again, you can see it's kind of easier to apply that power rule to understand what's going on. So I'm going to get f prime of x is equal to negative 4x to the negative third power minus 12x squared. It does say to rewrite with positive exponents. So I'm going to get f prime of x is equal to negative 4 divided by x cubed minus 12x squared. And that would be an acceptable answer. Okay, let's go down to the last two. Making pretty good time. We just have 10 and 11. We'll even make this a little bigger. So for number 10, we see that our function has a radical term in it, and the power rule doesn't really tell us how to deal with those. But we know that if we can rewrite a function with just exponents, then we should be able to apply the power rule. So we're just going to rewrite f of x without the radical. So I get 4 times x to the 2/3 power plus 5. Now if you're unsure of how I did that, this index here, this 3, goes in the denominator of our exponent, and the power on x stays in the numerator. So once we've done that, we can then go ahead and take the derivative. So I'm going to get f prime of x is equal to 8/3 x to the power of negative 1/3. So 2/3 minus 1 gives us negative 1/3. The derivative of the constant part of this function is 0, so you could write plus 0, or you can just leave it. And now we just need to rewrite this with positive exponents. So I get f prime of x is equal to 8 divided by 3 times x to the power of 1/3. This is a perfectly acceptable answer. However, on a multiple choice test, whether it's in this class or whether it's on your AP Calculus exam, the answers may be back to radical form. So you need to know how to convert this back to radical form in case those are what you have to choose from. So f prime of x could also equal 8 divided by 3 to the times the cubed root of x. Right? So we look at this exponent right here. The denominator ends up being our index, and the numerator ends up being our power on the x inside the radical. So both of these answers are correct. You need to know how to do both, just in case you have to rewrite your final answer in a specific form. Okay, let's look at number 11, and then we will be out of here. This one we actually have more work to do than our other problems. We have to rewrite this function twice. The first thing I'm going to do is I'm going to get rid of the radical. Sorry, it's not going to be f prime yet because I got to rewrite. So I'm going to get rid of the radical in the denominator, and I'm going to get 5x divided by x to the 3/5 power. Okay, so again, we just talked about where those exponents are supposed to go. Now I need to try to rewrite this without a denominator. So if I think back to my exponent rules, if I have the same base in my numerator and my denominator, which I do, x, then I can just subtract the exponents. So I get f of x is equal to 5, because 5 divided by 1 is 5, times x to the 2/5 power. Now, you always want to think back when you're changing a function from one form to the other. You always need to think, okay, are my domains the same, right? And up here, notice that 0 was not in the domain, because then we would get our denominator would be 0, and then we get something that's undefined. Here, it is possible to substitute in 0 and get a real number. We would just get 5 times 0, which is 0. But that can't be true if our original was undefined at 0. So we just have to say where x cannot equal 0. Then it means that this f of x is truly the same as this f of x. So now they are the same once we've added on that qualifier. Now I can go and apply the power rule. So I'm going to get f prime of x is equal to 5 times 2/5 is 2 times x to the power of negative 3/5. Again, let's rewrite using positive exponents. So f prime of x is equal to 2 divided by x to the 3/5 power. Perfectly acceptable answer. If you wanted to rewrite it using radicals instead, certainly could. So we'd get f prime of x is equal to 2 divided by the 5th root of x cubed. So again, that denominator in our exponent becomes our index in our radical expression, and the numerator stays as the power to the base. Okay, so that's the end of the problems for this lesson. However, you're going to continue to practice this power rule, whether it be in homework sets or future lessons, and you're going to start to know it like the back of your hand, because again, you're going to use it in all of our units from here on out, and you want to have a firm grasp of how to use that and how to use this power rule in a bunch of different scenarios before I start to introduce new rules, right? Because we could see functions where you can't actually apply the power rule and you're going to need some other rule. So until next time, this is Mr. Fawcett. Enjoy the rest of your day, and I'll see you back here shortly.